Right. Well, let's try this again. Final starts off with some simple nomenclature questions. Again, the nomenclature covers alkanes, alkanes, alkynes, some dual functionality compounds, whatever. For our first one, we have an alkyne that's also an alkyl halide. Remember, the rule is for a alkene or alkyne, you want to give that the highest priority. That doesn't go for alkyl halides. Therefore, this is going to be carbon number 1. We're going to have 1, 2, 3, 4, 5 carbons in our compound. So it would be a 1-pentyne. And down here at carbon number 1, 2, 3, 4, 5, we have a bromine. Any questions? Next guy is a simple alkene. Again, we want to give our double bond here the lowest number. We would have a number 2 if we started here or here. This is going to be carbon number 1, however. We're dealing with 1, 2, 3, 4, 5, 6, 7, 8. So it's an octene. Double bond here in carbon 3. We have an ethyl group also in carbon 3. And we have a methyl down here in carbon 6. The next on the exam, it said no stereochemistry. I lied. I actually wanted you to do cis and trans stereochemistry there. I apologize for the error. This is a very simple cyclohexane. We're going to let this be carbon number 1 alphabetically. We have a bromine in carbon 1, a methyl in carbon 3. And what I wanted to do is make sure that you could do stereochemistry on these. We could also do RNS, but remember we did RNS for the take-home part. So we simply need to say this is a 1-bromo, 3-methyl cyclohexane. This is axial, that is equatorial, that makes them trans. Very simple, we're doing a cyclopentane. We need cis 1,3-methyls. Start off just with a basic template. We have things in 1 and 3. Cis simply means they have to be on the same side. So something like this works. Methyl up, methyl up. I'm sorry?
It's not on our test. It's not.
Oh, it's not? Oh. Well, gee whiz, it was supposed to be. Okay, well, watch it anyway. I guess I deleted that to make the page count. I don't know. So, this is a dimethyl cyclopentane. Here we have a trans 1-bromo 4-chlorocyclohexane. Again, what I would do in a case like that is to simply draw a template. If they're going to be trans, that means that they're either both going to be axial or equatorial. Because we want the most stable conformation, we want to make them both equatorial. So let's just start off putting our bromine here, our chlorine here, they're both equatorial, and fill in the hydrogens. All right, I think we're back to where we are here. I won't have to get to the... Gee, I hope I didn't delete the alkyne slide by accident. No, it's there. Okay. All right, so we're back on track. This is a synthesis problem, and there's one like this on the exam. There are a couple on the exam. This one is very simple. They're all one step. All you have to do is put in the appropriate conditions to convert this alkyne into these compounds. As you look at these, and remember when you're doing a synthesis problem on an exam, if you forget the details of the reaction conditions, just flip over to the reactions page, because pretty much they're all going to be there. We are converting this alkyne into a ketone. That means we are putting an oxygen, bonding an oxygen to this carbon. If you look at the two carbons of the alkyne, this is a primary carbon, that is a secondary. So this is a Markovnikov addition. We know we can do that by adding a hydroxyl group to this carbon to give this enol intermediate. Now, we all recognize that the enol is in rapid equilibrium with the ketone. The way this works, the base pulls off the hydrogen here, puts it here, and this converts into the ketone, looking like this. Our reaction conditions are simply mercury with aqueous acid. No problem with the rearrangement. Mercury kind of sits on here, we form a mercurinium ion, it falls apart by itself, and we wind up with the ketone. Any questions? Our second compound, we have elaborated this chain. We've added a group out here. The group we've added is simply a methyl group. We know we can do that by converting the alkyne into an anion, and then using that in this simple SN2 reaction. The group that we need for our SN2 reaction must have one carbon and a leaving group. Therefore, if we do sodium in liquid ammonia, previously dissolved, that makes sodium amide, very strong base. That will give us the anion. Step 2, use bromomethane. That's a good example for electrophile. The anion will attack the carbon, bromine leaves, and we wind up with our extra carbon on our chain. Our next one, we simply have done a partial reduction of our alkene. Now we know two ways to do that. We can do Lindlar catalyst in the presence of hydrogen. That gives us a cis addition. We can do dissolving metal reduction, something like sodium liquid ammonia or lithium liquid ammonia. That would give us a trans reduction. However, we have two hydrogens here, so it doesn't matter if it's cis or trans. We could use either one. So either hydrogen and Lindlar, or something like liquid ammonia with lithium or sodium. And finally, again, we're making a carbonyl. This time it's going to be on the primary carbon. So that's anti-Markovnikov. We know we can make an anti-Markovnikov alcohol by doing hydroboration oxidation. The anti-Markovnikov alcohol would look like this. Again, this is an enol. Enol is going to rapidly convert to the carbonyl. In order to make this, we simply need hydroboration, oxidation, 2 steps. And once again, make sure you know the mechanism of this. Pull the hydrogen off, make a double bond, put the hydrogen here, and you make the aldehyde. Any questions? All right, simple reactions. If we take permanganate in the presence of acid, we remember that that is going to split a double or triple bond. We're going to split it right in the middle. These two alkene carbons have a hydrogen attached. If we simply split it and made each one a carbonyl, that would be aldehydes. As soon as you make an aldehyde, however, in the presence of permanganate, it's oxidized to a carboxylic acid. So, each of these carbons is going to be a carboxylic acid. You could draw it like that, or you could open up the chain and make it look a little more attractive. Remember, we have 1, 2, 3 CH2s in between, so it would look something like that. 1, 2, 3 CH2s. Hydroboration oxidation with an alkyne. We just did that one, didn't we? Here we are going to make an enol. The OH is going to go to this carbon. It's going to undergo rearrangement to give us an aldehyde. We have hydrogen attached. That means we wind up with an aldehyde. Here's our enol. Again, the OH is attached to the anti-Markovnikov or primary carbon. This rearranges to give the aldehyde. How simple can you get? HBr, that's Markovnikov addition. We have an alkene with a secondary and a tertiary carbon. And we will form the carbocation on the tertiary carbon. Bromide anion will add, and we will make this as our product. Here we have an alkyne. We have sodium and liquid ammonia. This is dissolving metal reduction. We remember that that goes stepwise. It's a radical reaction. And because of that, we get the most stable alkene, which is typically the trans alkene. So this undergoes reduction. We simply wind up with our trans alkene. Ozonolysis is going to split our double bond. Unlike permanganate, however, aldehydes are stable. So whatever is attached to the sp squared carbon stays there. We simply make each of these sp squared carbons into a carbonyl. Our first one is going to have the benzene ring. Our benzyl carbon here is going to be a carbonyl. It has one hydrogen attached, so it would look like that. Our second carbon is going to be a carbonyl with two hydrogens attached, and it looks like that. Sodium amide. Sodium amide is sodium previously dissolved in liquid ammonia. It's a very strong base. It's going to react with our alkyne here to make the alkyne anion. The alkyne anion is going to be a nucleophile in an SN2 reaction. The electrophilic carbon is here. That's our benzyl carbon. Bromine is our leaving group. The reaction simply is this electron pair attacking this carbon, bromine leaves, and we add the two together. Here's the original 3 carbons of our alkyne. This is the bond that we just made. Any questions? Hydroboration oxidation again. You know this is going to be anti-Markovnikov. Now this really isn't a great exam question, not for 234 anyway, because both of these are secondary carbons, aren't they? So you could put the hydroxyl group on either one. Turns out that one of the main factors in hydroboration has to do with steric bulk. The bigger it is, the further the boron wants to be away from it. So in this particular reaction, this secondary carbon will be favored, and we'd wind up with this alcohol. HBr peroxide. We have a secondary carbon, we have a tertiary carbon. HBr peroxide is a radical reaction. We're going to get an anti-Markovnikov alkyl bromide. This is the carbon that would accept the bromine. So bromine radical will add here. Our most stable tertiary radical would be there. And that would be our product. The real joy of this as an exam question is watching people try to draw the bicyclic compound.
Small issues. Small issues.
Here we have an alkene and an alkyne. We have hydrogen in the presence of platinum catalyst. We know that in the presence of platinum, we can reduce an alkene all the way to the alkane. Likewise, the alkyne is also reduced to the alkane. So in this case, we're going to reduce them both and simply make this alkane. Any questions?
Sorry, what'd you do there? I don't understand.
Well, if we just had the triple bond and hydrogen, we would make an alkane, right? If we just had a double bond, hydrogen platinum, we would make an alkane. So all we do is add 3 moles of hydrogen here, 1, 2, 3, to make this guy.
So you do it to both of them?
Now, sodium in liquid ammonia, dissolving metal reduction. We know that that will reduce an alkyne, but it does not reduce an alkene. So there's some selectivity there. This is going to give us the trans alkene. So this guy is reduced to a trans alkene, which means the product is our conjugated diene. Here we have diiodomethane, zinc, copper, amalgam. This is going to introduce carbene. Carbene is simply CH2, neutral, and it's going to add to the pi system here to make a cyclopropane ring. All you have to do is draw your 5-member ring with a cyclopropane ring attached. Obviously, these two must be on the same side because the cyclopropane occupies the other. Now on the exam, a lot of you messed up this type of problem. Remember, if we're going to do an E2 elimination, the leaving group, in this case the iodine, and the hydrogen that's pulled off must be trans or anti to each other, and they must be in the same plane. So that's called enterophation. So, simplest way to do this one is to just redraw it. Something like this. Again, ethyl and hydrogen coming up, methyl and methyl coming up. Here's our hydrogen. We need to rotate this so it looks like this. Now our base is going to come in, pull the hydrogen off. As it does, we'll make our double bond, the iodine will leave. It's an E2 reaction, so it's all concerted, no intermediates. Note here that our methyls are on the same side. This is the compound that we would get. All right, these first two are just simple SN2 reactions, aren't they? When you have an SN2 reaction, what you need to do is simply identify your nucleophile, your electrophilic carbon, and your leaving group. The nucleophile here is going to be the oxyanion, O-. It has the electrons. This is going to be our positive carbon. And bromine, of course, is our leaving group. All in the world that happens is the oxyanion attacks this carbon, bromine leaves, we wind up with an ether where the oxygen is bonded to our electrophilic carbon. Next one is the same thing, just a different nucleophile. This oxyanion will attack. This is our electrophilic carbon. That's the leaving group. Bromine leaves, and we wind up with the carboxylate ester. The O- bonded to our electrophilic carbon. And finally, a reaction we all love. Make sure you understand this sort of thing for the final, the mechanism of it. NBS carbon 10 light. Light means we're going to make radicals. Remember, when you have a compound like this, the sp cubed carbons that are adjacent to a double bond, so these two guys, are referred to as allylic carbons. They form very stable radicals, and so this gives selective bromination at either of these carbons. All we're going to do is make a bromine radical, add it to one of those, and this is our product. Simple SN2 reaction. Here we're using a sulfur nucleophile, but it's just like we used oxygen, doesn't matter. Our electrophilic carbon is going to be this guy. Chlorine is our leaving group. The sulfur anion attacks the electrophile. Chlorine goes, we make a bond between the electrophilic carbon and the sulfur. AHBr peroxides. Again, this is a radical reaction. We will make an alkyl bromide with anti-Markovnikov Leaching chemistry. We have a secondary carbon and a tertiary carbon. That means the bromine will bind to the secondary carbon, anti-Markovnikov, and that is our product. And finally, hydrogen with Lindlar. Remember, Lindlar stands for lousy. It's a lousy catalyst. It's a poison catalyst. And because of that, we get only partial reduction of our triple bond. Just like catalytic hydrogenation of an alkene, though, the hydrogen goes on from the same side, which means we wind up with the cis alkene. Two hydrogens go on here and here. Any questions? All right. Here we're going to do a reaction. These are all going to be elimination. And we're going to name our product. So a two-step question. This is going to be an E2 elimination. Bromine is our leaving group. We want to form the most highly substituted alkenes. So we're going to eliminate across this bond. This is the hydrogen that's going to come off. This is the bromine that's going to leave. Our base is going to pull off this hydrogen. The electrons will come in to make our double bond. This bromine will leave, and we simply make the alkene. Any questions? Now this, oh, let's name it. I forgot. Remember, when we're going to name this stuff, we must, it's a cycloalkene. So that means that carbons 1 and 2 must be the alkene carbons. We must start at carbon 1, proceed through the double bond. This is carbon 1, that's carbon 2, so we have a 1-methyl cyclohexane. All right, this guy is just like the one we saw earlier, except different. Again, we're going to do an E2 elimination. We want to form the most highly substituted alkene. Let's go ahead and redraw it. We have hydrogen and methyl up, hydrogen and ethyl up. This is our leaving group. So we're going to have to rotate this so that this hydrogen is anti and coplanar. So I'm just going to rotate this a bit. Now, a base can come in, pull off this hydrogen, we'll make our double bond, leaving group will leave. And as far as the stereochemistry, just look at it carefully. Here our two ethyl groups are on opposite sides of our double bond, aren't they? So we would just draw this like that. Two ethyl groups on opposite sides. If we named it, our longest chain would be 1, 2, 3, 4, 5, 6. So it's a hexene with a double bond at position 1, 2, 3. A methyl group at carbon 3. Our stereochemistry here, our main chain is trans, that's E, 3-methyl, 3-hexene. even though we've done stereochemistry on the first part, do remember E and Z, cis and trans for the final. And our last one here. Once again, we're going to be doing an elimination. If you look at our, we know that this is our leaving group, and this is the hydrogen that has to be pulled off. Now we could do the same thing we did in the previous one. We could rotate and whatever. But if you look at what we're working with, we only have methyls here, don't we? So regardless which direction we rotate this thing, we're going to get the same product. So we don't have to be compulsive. We simply pull off the hydrogen, rotate the bromine so it's down, puts the methyl group there, and we wind up with this as our product. This is going to be a 1, 2, 3, 4, so it's a butene with a methyl group in carbon 2. All right, now this is a nice, simple little synthesis problem. I hope everyone got this. We're making an ether here. The only way we know to make an ether is by an SN2 reaction. Now in the SN2 reaction, an oxyanion is going to attack an electrophilic carbon. So we're going to make a bond from the oxygen to a carbon. We want two ways. Therefore, what you have to do in a case like this is say, fine, I'm going to split my oxygen-carbon bond at one of the sides. Doesn't matter which one. We'll do this one first. And we say, what do we need in order to make this by an SN2 reaction? Well, the alkoxide has to be everything on this side, isn't it? As an O-. This is the electrophilic carbon, so here we need a leaving group of some sort. Here's our oxyanion, that's this guy. Here's our electrophilic carbon. I put a bromine on for a leaving group because it's easy to spell. And that one will work. For the other pathway, we're simply going to split at this side. So our oxyanion is everything on the left here. This is our electrophilic carbon. That's where the leaving group used to be. And we could do that with this pair. Here's the oxyanion. Here's the electrophilic carbon with a leaving group. Question? Any questions? All right, simple multiple choice. There is a page of multiple choice on your final. Which of the following is true regarding SN2? Rearrangements commonly occur. No, that's not true at all. It's a concerted reaction, no intermediate. Intermediate radical, didn't I just say no intermediate? Most stable carbocation, that would be an intermediate. None of these are true regarding an SN2. It's concerted, no intermediate. SN1. When you do an SN1, do you also get E1 eliminations? Sure, because they both involve exactly the same carbocation. It's a very messy reaction. Rearrangement is common, absolutely. When Whenever you have a carbocation that can rearrange, it will. It's favored by polar protic solvents. You have to make an ion. Polar solvents favor ions. All of these are correct. E1 elimination. Remember, with an E1, we're going to make a carbocation. That's going to lose a hydrogen, so it's a stepwise reaction. Because of steric effect, the least substituted alkene is formed. Well, that's nonsense. Side-step would be upset with that one. Always go for the most highly substituted. Elimination occurs antiperiplanar or trans. No, that's an E2 elimination. Sterically hindered base favor elimination over substitution. That's true. Remember, we always use tert butoxide. Big thing with an O-, difficult to get in for substitution, works fine for elimination. This is our proper answer. Hydroboration of an alkyne. Answer 1. Alkaline peroxide will yield an aldehyde. Remember, this is going to give us an enol, isn't it? The enol, the oxygen will be bonded anti-Markovnikov, and there's a hydrogen here. So that's going to give us an aldehyde. No way we can get a ketone. We don't get rearrangements either. Boron intermediate, boron's bonded to the benzyl. No, the boron is at the same carbon that lines up with the oxygen, which would be out here. So this is our proper answer. This one's kind of cute. We take a compound, we do permanganate oxidation. We wind up with an acid and CO2. So what kind of compound was it? Was it tetrasubstituted, disubstituted, trisubstituted, or terminal with one alkyl substituent? Or this guy? Remember, we get CO2 whenever we have a CH2 group. To get a carboxylic acid, that means we need a hydrogen. If we took a generic compound like this, and we split it here, this would turn into the carboxylic acid. This guy would turn into CO2. We could describe this as a terminal alkene. That means an alkene at the end of the chain with one substituent. All right, because this is the final, we have very simple questions going all the way back to the concept of isomers. That's why final exams are so easy. For this, we simply need to, number 1, do a formula. We know if they're going to be constitutional isomers, they have to have the same molecular formula, just different connectivity. This is C6C7H12. C567H12. C6, 7, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. And this guy is C1, 2, 3, 4, 5, 6, 7. However, only 10 hydrogens. So A, B, and C are all isomers. Conformational isomerism is on the exam too. When we have a cyclohexane ring, in general, the most stable conformational isomer will have the greatest number of equatorial. Again, that's good. Equatorial are good. Ring inversion requires rotation around carbon-carbon single bonds. Nope, it's a ring. You can't do that. Equatorial substituents are disfavored due to eclipsing. No, that's axial. Axial substituents eclipse. Therefore, this is our best answer. Finally, in its most stable conformation, 2 methyls are axial, 2 are equatorial, all are axial, all are equatorial, or none of the above. What I would do is simply take this boat and convert it to a chair. What I would do is kind of start off with this and say, what I'm going to do is take this carbon, bring it down. I've got substituents here. If I put these in, it would look like that. Now the only operation I have to do is to take this carbon, move it down. When I do that, I have 2 equatorial methyls and 1 that is axial. Remember our friend, the Newman projection. Simply convert this guy into our Newman projection. We are told in the problem, carbon number 4 is the front, 3 is the back. So let's number it. This is going to be our front carbon, that's this guy. 3 is our back carbon, that's this guy, the big one. All right, attached to 4, we have 2 hydrogens here and a methyl. Put them in like that. Attached to carbon number 3, we have 2 hydrogens and isopropyl group. We want the most stable, so we're going to put it down here opposite the methyl, looking like that. All right, remember how to do formal charges? Again, back in chapter a long time ago. Just say no. Now the trick with nitrogen monoxide, frankly, is drawing the Lewis structure. If you think about it, nitrogen is in group 5, oxygen is group 6. So we have 11 valence electrons. Oxygen is more electronegative, so we're going to give it the full octet. 11 is an odd number. That means that nitrogen is going to have only 7 of them. The Lewis structure then would look like this. There's our octet. Nitrogen has 2, 4, 6, 7. So this is what it looks like. Now remember the rule for doing formal charges. we're going to split all our covalent bonds. Then we're just going to add up the number of electrons there are around each atom and compare it to the atom in the periodic table. For nitrogen, this is group 5, so we should have 5 valence electrons. It has 1, 2, 3, 4, 5, which means it's a 0. For oxygen, group 6, we have 2, 4, 6, which means it is also a 0. Any questions? If we had put our lone electron over here on the oxygen, then we would have 6 electrons here, 5 electrons here, and we would have charges. So that's why this is a more stable structure. All right, finish up here with just a couple transformations. We want to draw these cyclohexanes in their most stable conformation. We look at this and say, oh my goodness, there's a terbutyl group here, and it's axial. We know that it must be equatorial. Therefore, we're going to draw a chair, and we're going to put this terbutyl group equatorial. When we do that, everything that's axial will become equatorial, everything that's equatorial will become axial. Therefore, this methyl, axial, becomes equatorial, equatorial becomes axial. Once again, we know that this terbutyl group is going to have to be equatorial. So we're going to take our basic 6-membered ring. We have substituents at 1 and 4. This must be equatorial. That means this methyl has to be axial. If you want to think about it this way, this methyl is coming up, this one's going down, isn't it? Therefore, if this one is axial, this one must be equatorial. Oh, I said that wrong, didn't I? This one's up, this one's down. They have to be trans to each other, I'm sorry. So if this one's axial, this one must be axial as well. Both on opposite sides. This is axial, this must be also. We have 2 axial bromines. We must convert those to equatorial. If these become equatorial, the methyl group becomes axial. So here's our 1,3 skeleton. Our 2 bromines must be equatorial, and our methyl must be axial. And our last one here. As we look at this, we have a bromine up, a methyl group down. So these are going to be trans to each other. This bromine is up, and this one is down. Once again, they're trans to each other. We want to try to get our big bromines equatorial as best we can. So if we look at these 2 bromines, they're trans. That's going to make them di-equatorial. I'm sorry, this is 1,3, so axial equatorial, not diequatorial, that'd be 1,4. For this guy, we have up and we have down, they are trans. This is the one that is diequatorial. Sorry about that. Now, one more time. Our bromine here is up and down, that's trans. For 1,3, trans would be here and here. For 1,4, these two are trans, it would be equatorial, equatorial, and that's their structure. Now, most of this is old stuff. There are reactions, there are SN2 reactions, there are eliminations. Remember, you also need to know the free radical chain mechanism. A lot of you messed up on that on the final. I'm sorry, the third exam. Don't mess it up, it's simple. Also make sure you can do something like addition of HBr with carbocations, rearrangements, and stuff like that. Most of you did well on that on the third exam. Any questions? All right, well, it's tomorrow. I have been recording this, hopefully. So if you want to go over it again, I will get this up on YouTube as quickly as I can.